Hi guys, let's continue. Okay, sorry for the delay. Okay, so that was a little bit of a fun, presentation for you to get a feeling how the compiler can be used. Now let's get back and talk a little bit about parallelization. This is more like a standard topic, although it's still quite advanced, I have to say. Okay, so to understand ability to parallelize code, we need to define something called data dependencies. So let's say we had a simple linear piece of code with statement S1, S2, S3, and S4. Like that, you had A equals 1, B equals A plus 2, A equals C minus D, A equals B divided by C. We defined 4 types of data dependencies, and you'll see that they had real meaning. First is the flow or true dependence. This is the easiest and the most important type of dependence. Is essentially if statement Si precedes a statement Sj in the execution, and Si computes the data values that are needed by Sj. So for example, A generated here would be needed here, right? This is a true dependence. This thing has to be followed by this. This is a true or flow dependence of the flow graph dependence, okay? It implies this type of dependence that the instruction has to be ordered. Si must execute before Sj, okay? And there are different notations that people use. It's called, as I say, true or flow dependence. This is how you write. So here, for example, S1 and S2 had a flow dependence on A, right? And also S2 and S4. So B is generated here and B is needed here, right? So these two, there is dependence here and dependence here. And this is the notation. S1 has a dependence, flow dependence on S2 and S2 on S4, okay? Another dependence is called anti-dependence. Anti-dependence, that's when a statement Si precedes a statement Sj in the execution, and Si uses a data value that Sj computes. So here it's the other way around. It's, for example, if you look here, this is generated A, and this is using A, right? And they go in this particular order. So that's called an anti-dependence and has like sigma A notation. So that doesn't necessarily mean they cannot be reordered, but you can just blindly move this over this, because then this will start to use a different result, right? So that's why it's called anti-dependence. Okay, it's the opposite of the flow or true dependence. There's another dependence called output dependence. It's when the outputs are the same, like this or this. And this is all about dependencies that tells you I can just take this and move it, right, over in other instructions, right? I can just reorder things, so it depends. That's an output dependence. And there is also so-called input dependence, which is the weakest of all because it doesn't really preclude anything. So the input dependence is, for example, if C is used here and C is used here, they depend on the same input, right? It's sometimes a useful piece of information, but it doesn't limit me in reorder these instructions, okay? So this is a 4 possible dependencies, right? Flow dependence or true dependence, anti-dependence, output dependence, and input dependence. Any questions? Those are just definitions of dependencies. We will use them to define something called dependence graph.
If we use SSA, do we still have output dependence?
You're going to see this is the dependence graph is different from the flow graph, right? The flow graph is what the SSA is used for, right? But there is a relationship. So like, for example, if in SSA form, some of these dependencies might go away. But remember SSA, like we're going to use data dependencies for, say, arrays, representation of different iterations of array. SSA cannot handle that. Like SSA cannot easily represent dependencies of things in the flow graph between different variables of the same array, like A0, A1, and so on. We're gonna need that dependency graph as another structure. So the short answer is there is a relationship between data flow and data dependence. They're not completely independent concepts, but they can be used for different problem solving. And sometimes one is better, sometimes another better. For example, something like this problem, like the only real dependence that would stay in SSA would be the true dependence, because everything else can be solved with renaming, right? Right. So if you would have this piece of code, you can just rename. This A becomes A1, this is A2, and a lot of these problems go away. You can do this for variables. You cannot do this as easily for elements of the array. Okay. So I'm defining you a simple concept, but now soon it will be used in a more complicated setting. It's a very good question, though. Anyway, so this is essentially leads to a data dependencies where essentially there is some definitions here. There is a source of the dependencies, and there is a sink of the dependencies, the direction. The only real true dependence is flow dependence. The others can be solved with renaming, as I just told you, right? So that you can get rid of a lot of those dependencies. In fact, that's what hardware does, right? They can break out some of those dependencies on the fly, which is easy when you just deal with scalars. So anyway, assuming there is no renaming for whatever reasons, normally we would define a dependence graph for this code segment this way. This is statements S1, S2, S3, S4, and then there is dependence graph. You see the dependence graph it's a directional graph, right? So for example, S1 has a true dependence with S2, S2 has an anti-dependence with S3, there is an also output dependence here, there is also an input dependence here, another outputs here, and another true dependence here, right? This is what the dependencies graph is about, right? It just literally follows these 4 different dependencies. Questions? Okay. So there are 2 ways that dependence can be defined. It can be value-oriented or location-oriented. So this is where things becomes interesting. So let's look at this little piece of code, right? Written this pseudo C or more like Fortran code, where you do add 3 iterations of the loop, right? And you have statement 1 and statement 2, right? So you see here, there is statements that this statement has iterations. That's what makes it complicated, right? So for different iterations, you had allocation in the code and you had the value that you computed each iteration. So you had S1 with index 2, S1 was index 3, S2 was index 3, and so on. This is separator shows the separations between loop iterations. What we care about is this AI here versus AI here. So as you can see, S1, 2 here using generates a 2 as its result, right? And then the second statement consumes it as its input, right? And so is true for all other iterations. That is a true dependence that was just defined between these 2 statements, right? What is interesting is that those, again, as I said before, S2 is the source of the dependence S2, and S2 is the sink of it. This is just we're applying our theory. The cool thing is here is if you look at this dependence in that graph, it doesn't cross the boundary of a loop iterations. It's a very important feature, as we are going to learn in the future, is if there's no dependencies between the loop iterations. It's an amazing thing. It means I can run these 2 loop iterations independently. So if those in my graph, if I can slice it such that loop iteration has no dependencies crossing that boundary, it means it can be independent, which, as you can guess, is an amazing feature for parallelization, right? It means in that array, I can run all these loop iterations completely independently. And that's an amazing thing. It helps solving a very fundamentally difficult problem of automatic parallelization, right? That's known to be, in general case, undecidable. Okay. So then the number of iterations between the source and the sink, here is 0 because it's all within the same iterations. You just take this iteration and the dependence direction is equal. So it just, it doesn't go backward or plus or minus. Okay. So this is the way the notation is used in this case. It's for loops. Let's look at something tiny little bit more complicated, right? I changed the index and now I had AI here and AI minus 1 here, right? If I would just look at the one loop iteration, these two things are different elements, right? There's no dependencies between them. But does it mean that there's no dependencies at all? It's not, because if you look, what happens, this generates A2, this consumes A1, this generates A3, this thing consumes A2. So it means there is this true dependence going in between two loop iterations and another one like that, right? So that means that there is instant S1 that precedes an instant of S2. In execution, S1 produce the data that's needed by S2. And this is a so-called loop carried dependence, right? That you see the cross. So it's like as you progress through the iterations, the loop is carried from iteration to iteration. The dependence distance here is just 1, because there is that dependencies between two loop iterations, and the direction is positive. So the dependence go into the positive direction. What it tells you, I can't just easily run this before I run this guy. But still, it has an important piece of information for me, because it kind of tells me that there is at least certain things I can do independently, right? I can, for example, slice the loop iterations and can do some other parts until these results are generated. Okay, so this is how it's written. Okay, this is just applying these definitions of dependency graph. Okay, any questions so far? Okay, let's look at another example. Again, I'm keeping it simple as possible for you so far. So we're going here, and now we're going with indexes going up. And you see the only thing I have here is an anti-dependency, right? So this is written here, right? You consume it here, and then you write it here, right? What does that mean? It means that even though those things doesn't really consume this value, I cannot just execute this loop iteration before this loop iteration, because then I would change what this guy is consuming, right? So there's still an anti-dependency. And I can just say, well, let's rename it, right? Because this is all the element of the same array. Okay, this is essentially also dependence. It's also loop carry dependence. Its distance is 1, but now this is an anti-dependence instead of a true dependence. So Frank, hopefully it kind of answers your questions why those dependencies we can just get rid of as with flow analysis, right? So you see that that's easy to solve when there's a plain text, but much harder with like, aggregate data structures. Okay. So things can get even more complicated if we go into 2 dimensions, right? So here I and j can change independently, and this is what you consume, this is what you produce, and here's our dependencies, right? In 2 dimensions. So you can use the same principles as before. In this case, S can be both source and sink, right? It produces and consumes. And it's the dependencies loop carried dependencies. And the distance is a vector 1 minus 1, because you keep, if you look at the true dependence here, it increases into the first dimension, 2 to 3, 3 to 4, but it goes down into the other dimension, right? So it's 3 to 2, here it's 4 to 3, here it's 4 to 3, 3 to 2, right? You see, right? So the dependence go into the direction 1 minus 1. And this is how you write this. Okay. Okay, so then the problem we try to formulate is having the simplest possible example with the loops, this perfect loop nest of the length D, where I had all these loop conditions, right, written. So this is essentially D depth nested loop with these accesses to arrays with different indices. The question we want to ask, if I had an array reference with like multiple different subscripts here, right? And this is a function applied for a subscript expression, and say those guys are all linear functions. What we want to say is when there is a dependencies versus where there's no dependencies, right? That's what the answer is saying. Like essentially, this is all needed, guess what, to do parallelization, right? We are looking at these nested nice loops, whether we can parallelize them or not. So if you assume that each subscript has a function and that function is linear, that's essentially the linear set of equations you need to solve, right? So essentially you will need to find all these cases where those indices would match, okay? So for example, this is an example of solving this problem. Let's say I have this loop. The question we want to ask, does there exist two iterations with vector I1 and I2 such that under this condition, we would get I1 equals I2 minus 1? And the answer is yes, there is 2 and 3, and 3 and 4, and there is a dependence, right? So it's a proven case that there is a dependence. Remember, when we do deal with dependencies, there can be three situations. No dependency, no loop carry dependency, proven dependencies, right here. And the worst case is maybe when we can't prove anything, right? And that's when means we need to be conservative and we can't assume anything. But here, we know there is a dependence. Moreover, we know the precise distance of that dependence. And when you know that, it's much better because you can have a scheduler that takes into the account the dependencies. Okay, but how about this case? Like remember where you go into the positive directions. So the question is, does there exist two iteration vectors, I1 and I2, such that they are between 2 and 4, because that's the limits, and such that I1 equals I2 plus 1. And the solutions exist. You get 3 and 2 and 4 and 3. And then you get, dependence like that, right? And the dependence distance vector is -1, right? But the question to you is this really possible in reality? Can you really have that happen? So the thing is, we might find the solutions, but those solutions might actually be invisible sometimes, right? So they're not necessarily satisfies the sum of the additional constraints we have above the variables of the loop iteration. So you need to be careful with when you verify the solutions. Let me show you another examples like that. So when you have a to I and a to I plus 1. So the question is there a dependence? What do you guys think? Are there any I1 and I2 where there's a solution for this? It's something like from high school. Okay, so on the one side, you had odd number and another one even number, right? So no matter when you know that I1 and I2 are integer, right? There's no solution to that, right? That means those things are always independent, right? There's no proven way that there's no dependencies. So essentially, in the general case, we want to formulate this as an integer linear programming problem of 2D variables and m plus d constraints. And then we need an algorithm that determines if there exists two iteration vectors, k and j, that satisfies these constraints, and it's called a dependence tester. And there's a dependence distance and all this definition. The idea is, literally, it's very simple. Here's my linear equations, how I can solve this properly, right? Remember, because this is an integer domain, right? The dependence distance in general case is NP complete, right? And if we can prove it, we said that to be exact dependence. Otherwise, if we can't prove it, is inexact. A dependence test must be conservative. If existence of dependence cannot be certain, the dependence must be assumed, right? So that's the usual correctness. And there is a gazillions of different dependence testers that are listed there. That again, we're not going to go over all of them. I've just shown some of those examples in the slides. You don't need to learn them or anything. If you're interested, you can look up in the slides and look for some examples. I'll just skip over the slides here faster. Another common one is GCD, again, that you probably remember from high school. So given the following equations, right, you want to find an integer solutions, and it only exists if and only if the GCD of A1, A2, and AN divided by C. So that's the conditions for the solutions of that to exist. The problem with the GCD test, it ignores loop bounds, gives no information on distance or directions of the dependencies, and it can result essentially in some false dependencies that claim something to be dependent, but which is not. But it's good in some simple examples like this, right? Like odd and even numbers. Yeah. So this is how you can simply solve this easy examples with GCD. So this is example where it doesn't work, right? So you see we have a distance of 100, and that's infeasible with the loop iterations going from 1 to 10. You never actually have that happen. But the GCD test is not that smart, so it's going to tell you that it's fine, right? And the problem is that's a false dependence. It's not real dependence. So that's not perfect because it cannot take the constraints into account. Okay, there can be all other different complications that, again, I don't want you to study today. There is like, loop iterations that are triangular, so it doesn't go like 1 to n, 1 to k. Like it can go dependent on I, right? So essentially, instead of going in a rectangular fashion over the loop iterations, you actually have a, triangular loop, right? When loop here depends on the loop iterations from the outer loop. And all that adds additional constraints that you need to solve. And there are like all these other different complications. So this is a generally known complicated problem. I just try to outline you and show examples why it can be complicated, right? As the use of other variables and known loop bounds, something that comes from the function parameters. This is what makes dependence detections a complicated thing, right, to do. And, there are even more complications with scalar variables. Again, I'm going to omit that. Okay, so this is just list all the other, like gazillions of different complications if you want to go in this route. All of that is done with one magic goal, is because you want to do loop parallelization, right? So essentially the loop can be parallelized if we essentially don't have any dependencies that are carried by the loop. So it's loop independent. Remember, as in the first examples, where the dependency was going within the loop iteration and was not crossing the boundaries of loop iteration. So that was relatively simple, okay? So essentially for the code like that, what we need to do, we need to look at all their, dependencies, right? Like here, you're gonna get a true dependence across both dimensions, and they're all, loop independent, right? They're not carried across the loop iterations. Here you're gonna get one that's, carried. Here you're gonna get another one that carried, right? So, okay, so then at the end of the day, that's the dependency you get, and the idea is that the outermost loop will have a dependence, but then the iteration of a loop may be executed in parallel with another if and only if no dependencies occurred across the loop boundaries. Like for example, here, everything has to be executed sequentially, right? There is a strong dependence here between the loop iterations across the second dimension, and you can't really do much about it, right? So you can't really do anything here, but you have some chances. So there, if you look at this as a two double nested loop, then on the G dimension, I had a dependency, right? But if you look at the I dimension, I can parallelize on that dimension. So if I had a multi-dimensional loop, nothing prevents me to parallelize across this dimension because across I, those two things are independent. So I can execute this as one loop iteration and another one instant of that with I2, 3, 4, all independently, right? So instead of doing, trying to parallelize the inner loop, I can parallelize the outer loop because the outer loop does not had loop carry dependencies. So you see how tricky it can be, how many possibilities are here. So this loop cannot be parallelized in the inner side, but it can be parallelized on the outer side. Okay, any questions? Again, we are not, this is a very complex, loop parallelism is a very complicated thing. So this is like one of the advanced topic. I'm just showing you what can be done there and why it's important, right? It's not that we're gonna ask you to essentially solve the general problems, but it shows you the possibility of what can be done, okay? Okay, so there's another example here. Here, iterations of loop I must be executed sequentially, but the iterations of loop J might be executed in parallel. So this is the example of the loop that the inner parallelism is fine, but the outer parallelism is not, right? Okay, so this just shows you how those different loops can be executed and how they merge afterwards. And here's an example where everything must be executed, you know, sequentially, right? But one interesting problem here is the iteration of loop J may be executed in parallel here, despite all that. This is something for you to think about in the spare time on why is it safe. So here, despite that, there is still a possibility to do inner loop parallelism. Okay, so I'll just show you a few quick examples of different loop transformation that are possible. One is loop interchange, right? This one is changes the order of the loops to improve the spatial locality. Remember, we've seen this before in other contexts, right? So this is one of the examples of how we can flip the dimensions, right? Like this is so-called loop interchange. And if we can prove there's no dependencies, we can do tricks like that. Sometimes this loop interchange can improve the granularity of parallelism. The granularity of the parallelism depends. Sometimes you want fine grain, sometimes you want coarse grain. It really depends on the situation, and loop interchange can help with improving the level of parallelism. So you can see here, and I can flip the dimensions. And here, for example, there, I can do the loop, the outer loop, so I can just parallelize these independent things, which might be better for certain strategies. Okay. I'm going to skip over the loop interchange. I think this is just where that's legal, but when it's not. Another thing that is super important is loop blocking or loop tiling. Remember, I also show it for locality reasons. So the idea of loop blocking, instead of going, you know, fully horizontally and then go to the next, you know, line, you actually change there and slice the control loop blocks, slice it into sub pieces. And then you would go over pieces, this piece first and second piece first, and so on, instead of going over everything in this manner, right? Yeah, so that's the idea. This is loop tiling, again, very good for cache locality. You can control the tile size and make sure it resides in your, you know, cache. So that would be a better use here. Okay. Okay, I think those are pretty much the major techniques I wanted to show. I guess tiling and interchange we've seen in other contexts. This just keeps coming in the context of parallelization, right? That's an important strategy. You're going to see it all the time when you're going to use compilers like loop tiling, interchange. Those are the more things like unrolling are the most common optimizations you're ever going to use. Okay, so I hope that was a good summary of what you can learn on parallelization. Again, this is when you're going to prepare for your exams, we are not going to ask any super harsh questions on that, but still make sure you cover the material, you understand tiling and interchange. This is important concepts, right? So we can ask questions about them, right? And hopefully get a general feeling about, what can be done with the compiler, how complicated stuff can be done, right? Okay, this is pretty much what I have for today. Any questions? Okay, no question then. Thanks a lot, guys. It was a pleasure to have you in this, very unusual semester. And yeah, we still have an exam and you had still a tutorial with us. Oh, sorry, not a tutorial. You had still the last assignment, right? That we need to grade. But that's pretty much it. So I guess you have the date of your exam. We would be happy to to answer any questions you have on Piazza, right? So start preparing. Feel free to ask more questions, and always happy to help with Dojin.
Thank you very much for the lectures.
Yeah, thank you guys. So everything will be posted as usual, and hopefully you enjoy and learn a lot, and it will be helpful in your future career. So I guess I'll see you next time at the exam. Yeah, we'll keep you updated if there's any changes there, but right now you had to assume 8 to 11. Yeah. Thank you guys. Okay, bye.